Hello everybody, welcome back to the channel. I'm here with a Head Start to A-Level Chemistry video, and in this video we're going to be looking at Organic Chemistry Part 2. This is the organic chemistry that is only on the Triple Chemistry GCSE course. So if you did combined science, you will have missed out on this. I'm talking about things such as alkene reactions in more detail, alcohols and their reactions, carboxylic acids and their reactions, and also a little bit about esters too. In my first Head Start to Organic Chemistry video, I covered the basics of alkenes. For instance, their general formula is CnH2n. So in other words, double the number of carbons you've got, that's the number of hydrogen atoms you'll have. We explored how alkenes are unsaturated, which means that they've got a double carbon-to-carbon bond somewhere within their structure. I looked at how they can burn in combustion reactions, not quite as cleanly as alkanes do, and how lots and lots of alkenes can join together to make one long polymer chain in the polymerization process. What I want to look at in this video is the type of reactions that alkenes typically undergo, which are addition reactions. Now, the double bond in alkenes, I've already said it's very reactive. That's because there are 4 electrons in that double bond instead of the typical 2 that you find in a single bond. As a result of that, the carbon atoms in that bond can form new bonds to new atoms that aren't currently part of the structure. If we take a look at a typical alkenes, I'll draw ethene just because it's smaller. If we add something to that structure, what happens in the addition reactions is the double bond between the 2 carbon atoms partially breaks, meaning that temporarily the carbon atoms have only got 3 bonds each, and then they form a new bond, a 4th bond, to something extra that wasn't originally part of the structure, which I'm just calling AB here, where A and B are random atoms and their identity doesn't matter. And so both of the carbon atoms form an extra bond, one to A and one to atom B. And then what has to happen to finish this job is that the original bond between A and B has to be broken. And so that's the overview of an addition reaction. An extra molecule is adding on to the molecule with the double bond. An example of this for an actual molecule that does add on to an alkene is when you do hydrogenation of an alkene. You are adding hydrogen on to that double bond. This requires a catalyst. Typically that would be something like nickel, and we would see, for instance, propene adding on those 2 hydrogen atoms, one to the 2 carbon atoms that have the double bond, one to each of them, and we'd end up with propane as a product. So we have saturated our alkene and it's now become an alkane. Another example of an addition reaction is when halogens add on to the alkene molecule. You can see here I've got propene again, and we might add something like bromine, and what happens is bromine is diatomic. All halogens are diatomic, so Br2 is going to add on to this molecule. One bromine will add on to the carbon on the left-hand side, and the other bromine will add on to the carbon in the middle. That double bond breaks, and the bond between the 2 bromines also breaks. This is actually the test for unsaturation. If you add bromine water to anything that's got a double bond, that bromine water will decolorize. It will change colour from yellow to colourless, whereas if no double bonds are present, it will remain yellow. And overall, what we've done is turn our alkene into an organic molecule with halogens as part of it. It doesn't have any double bonds, so it is saturated, so we call this product a halogenoalkane. And finally, there is a hydration reaction, which is where you add water to an alkene. The exact same principle is applied here. It's a little bit more complicated because you're adding more than 2 atoms onto the alkene, but we've got water, which I've drawn in its displayed formula here. This bond between the oxygen and the hydrogen in water is going to break, and then new bonds are going to form between the carbon on the left and the oxygen that's still got the other hydrogen attached to it, and the other hydrogen is going to join onto the other carbon from the double bond, and of course the double bond is going to break and become a single bond. And so overall, we are turning our alkene into an alcohol because you've got this O to H group within this product. I've just mentioned that alkenes can be turned into alcohols, and alcohols is something that we need to look at further now. I've drawn the first 3 alcohols in the homologous series, And these are displayed formulae. That's meaning I'm showing all of the covalent bonds in the molecule. If we take a look at how we name the alcohols, the first part of it is always the same sort of core of any organic molecule. How many carbon atoms are there in the molecule? Well, the first one has just got one, so its name begins with meth. It's a saturated molecule, no double bonds anywhere, so it's an, like alkanes, has got the an part. And it's an alcohol, so it is ol. So this first one is methanol. The second one has got a carbon chain of 2, so that's going to be eth or eth. It's saturated as well, so an-ol. The third one is 3 carbons in a chain, so that's prop, an-ol. And then it continues butanol, pentanol, hexanol, etc. Now, in terms of the formulae, we do sometimes show them not in full displayed. We give what's called the structural formulae, and that's where you take the carbon atom in the chain one at a time and sort of list what is connected to it. So if we go back to methanol, the carbon on the left-hand side has got 3 hydrogen atoms attached to it. And so when we're writing the structural formula, we begin with CH3. And then we've got the OH group that makes it the alcohol. That's called the functional group for the alcohol family. And so we finish with that functional group. CH3OH is the structural formula. In the same way, ethanol, the carbon on the left, has got 3 hydrogen atoms attached to it. The carbon in the middle has got 2 hydrogen atoms attached to it. And then you've got the OH on the right-hand side, and that finishes the structural formula of ethanol. And approaching propanol in the same way, we've got CH3 on the left, CH2 in the middle, then comes a CH2, and an OH finishes us off our structural formula of propanol. And so these rules just continue as you lengthen the alcohol chain. We also need to know some properties of alcohols. The first and foremost, alcohols burn really well. They produce carbon dioxide and water in the same way that alkanes do. The extra trickery here is just to watch out for when you're balancing a combustion equation for methanol, for instance, is that there is already some oxygen in the methanol itself. And that means that we don't need quite so many oxygen molecules to balance this equation for complete combustion. And the fuels, methanol, ethanol, propanol and butanol, are all used to provide energy in different situations, whether that's in spirit burners when you're camping, or whether that's as a replacement for petrol in car engines or factories, but they do burn very well and produce lots of energy. Further uses of alcohols include dissolving them in water to make neutral solutions. That means it will have a pH of exactly 7 because there's no hydrogen ions dissolved in the water and no hydroxide ions dissolved in the water. This is one of the reasons why ethanol can be produced as an alcoholic drink. It isn't toxic in the way that methanol would be toxic. Methanol can actually be fatal or cause blindness if methanol is drunk, but ethanol can still cause liver damage if drunk to extremes. Not only are alcohols soluble in water, they are actually good at dissolving other things that water can't dissolve. And so that means that ethanol will be very useful in things such as perfumes and aftershaves because they dissolve the oil that then gives the aftershave the smell, whereas water wouldn't dissolve the oil very well, but actually water does make up a large part of the aftershave because it will mix well and form a solution with the ethanol. So the ethanol dissolves the fragrance and then the water mixes with the ethanol to provide one perfume or aftershave solution. Additionally, they will react. If you were to drop sodium into ethanol, for instance, it would react in a very similar way to dropping sodium into water, in that the sodium would float on the surface of the alcohol and you would produce some hydrogen gas as a direct result. Additionally, alcohols will oxidize. That means they will react with oxygen from the air. Once that happens, the alcohol will turn into a carboxylic acid. More about them in a moment. We explored how alkenes can be turned into alcohols, and that is done on an industrial scale to produce alcohol that's going to be used as a solvent or as a fuel. But in terms of drinking the ethanol that's been produced, that is far more commonly produced by fermentation of sugars. And in this process, the sugar is mixed with yeast at about 37 degrees C, and the yeast acts under anaerobic conditions to produce ethanol and also carbon dioxide as well. This process is considered to be carbon neutral to an extent. And what that means is the sugar has come from plants, the plants took carbon dioxide in when they grew, and so then if we were to, for instance, burn the alcohol that has been produced from a fermentation reaction, the carbon dioxide that was released during the combustion would be exactly equal to the carbon dioxide that was taken in when the plants grew initially. So that's what they mean from the point of view of carbon neutrality. There is no net increase in carbon as a result of burning alcohol that has been produced in this way. I'd like to just stretch us a little bit by considering something that is very much A-level chemistry content. If we look at propanol, propanol has got the molecular formula C3H7OH, which we could actually have just written C3H8O, but that wouldn't have given us any clues that it was an alcohol. The presence of the OH group is what makes it an alcohol, and we've recognised that in the formula. If I was to ask you to draw propanol, there's a good chance that you might draw a different thing to what I was imagining, and that's because there are two different forms of propanol. I'll show you them both here. What you can see is the top propanol that I've drawn has got the O to H group on an end, and then the one underneath has got the O to H group in the middle on the second carbon atom in the chain of three. And so these are both propanol, but they're both different. And so we need a slightly different way of naming them. They're what's called position isomers, because the O to H group is in a different position on one chain to the other. The first one has got the carbon atom on the end with the O to H group, so that's carbon in position number 1. And then in the second one, it's on the second carbon, so position number 2. So we call the first one propan-1-ol, written like this. And then the second one is propan-2-ol. You might think that there would be a propan-3-ol if the OH was on the right hand of the 3 carbon atoms, but these molecules are not static. They can move around, they can twist, they can flip over. So if we were to have a propan-3-ol, all it would be is exactly the same as propan-1-ol, just kind of turned around or rotated, or however you want to think about it. So position isomers, something you need to know about for A-level chemistry. And so they're called isomers because they're made up of the same parts, iso meaning the same and mer meaning parts, but position. What that means is the functional group is in a different position on the carbon skeleton. So even though they've got the same parts, they've got a different position for the functional group, hence position isomers. The next homologous series, the next family of chemicals that I want to talk about, are carboxylic acids. And carboxylic acids have got the functional group COOH somewhere within their structure. They might have a lot more to their structure, but that group will be present somewhere. And then the simplest carboxylic acid is the one that I've shown at the top here, and it has got just one carbon atom in its chain. So we know that its name is going to begin with meth. And it is methanoic acid, is this carboxylic acid. And then the second carboxylic acid has got 2 carbon atoms in its chain, so that's going to be ethanoic acid. And then it becomes propanoic acid, butanoic acid, pentanoic acid, etc. The structural formulae for these acids is no more complicated really than the alcohols. For instance, the first one, we've got the hydrogen on the left-hand side, and then we've got the COOH group. And so that's the structural formula for methanoic acid. Ethanoic acid is CH3 for the left-hand carbon, and then COOH. So you can see they're really similar, the displayed formula and the structural formula. Structural formula is definitely faster. Displayed formula definitely gives you more clarity about how these atoms are actually bonded together. Now, carboxylic acids are referred to as weak acids. All acids dissolve in water to produce hydrogen ions, that means H plus AQ, in solution, whereas hydrochloric acid and sulfuric acid will dissolve fully and produce a huge number of these hydrogen ions when you put them into water. Carboxylic acids don't. Only a small proportion of the ethanoic acid, for instance, will actually dissociate and become ions. Sort of 1 in a million, or maybe even fewer, of these acid molecules will actually fall apart. As a result of this, carboxylic acids do what you'd expect any acid to do, but less vigorously. For instance, they will react with a base, just like any acid would do. So if you were to react ethanoic acid with sodium hydroxide, you would produce a salt and water, because acid plus base makes salt and water. The name of the salt would be slightly different to chloride and sulfate, etc. But the name is, once you get used to it, the name is quite straightforward. What you make is you make a carboxylate salt. So for instance, methanoic acid reacts with sodium hydroxide and we make sodium methanoate. If we'd used ethanoic acid, we would have made sodium ethanoate. So acid plus base makes salt and water. Additionally, carboxylic acids would react with metal carbonates, just like sulfuric acid would have done. And it would fizz, we'd get carbon dioxide produced, we would make a salt, and we'd make water. So propanoic acid plus calcium carbonate would make calcium propanoate plus carbon dioxide plus water. This is actually used as a test for carbonates. We can add a carboxylic acid to a solution that we think might contain a carbonate, and if we get this effervescence, this fizzing that carbon dioxide produces, we can be confident that the carbonate ion was present in the first instance. And then the final reaction that you need to know about in terms of what carboxylic acids can do is they can actually react with the alcohols that we looked at earlier and produce a new family of chemicals called an ester. Not only does this happen, we also make water as a byproduct. So a carboxylic acid plus an alcohol will react and turn into something called an ester. For instance, ethanoic acid reacts with ethanol and we produce ethyl ethanoate. This takes place usually with an acid catalyst such as phosphoric acid or concentrated sulfuric acid, and we can produce a whole range of different esters just depending on which alcohol we combine with which acid. You don't actually need to know all that much about esters from GCSE level. You pretty much just need to be able to recognise an ester. So what I'm going to do here is just show you how the esters formed. So here is ethanol on the left-hand side and ethanoic acid on the right-hand side. I've drawn the two functional groups near to each other because they're going to overlap and react together. What happens is the O to H group from the carboxylic acid and the H of the OH group of the alcohol, they react together and we produce the water. And then the carbon atom from the carboxylic acid and the oxygen from the alcohol don't have the correct number of bonds anymore. They've got one less bond each. And so what happens is a new bond forms between the oxygen of the alcohol and the C of the carboxylic acid, and we form a new link. And this overall is what's called an ester link. So the ester that forms is shown now on the right-hand side, and the COOC group is characteristic of an ester. If you see that cluster of atoms, that functional group it's called, this is an ester. And this ester is called ethyl ethanoate. The names are taken from the length of the alcohol chain first, and then the length of the acid chain. And this bit that I've underlined in each case, that just gets changed depending on how long the respective chains were. If we'd used propanol, it would have been propyl. If it had been methanoic acid, it would have been methanoate. So propyl methanoate. That's the only changes that get made to the esters' names. So easy-ish, but so similar, it actually can be confusing if you're not paying close attention to the names of the alcohol and the acid. And it's that order, alcohol, acid. There's one last type of isomerism, and that's called functional group isomers. To illustrate this, let's consider the formula C2H4O2. If I said, draw this molecule, and you have to obey the rules that carbon must always have 4 bonds, hydrogen only 1, oxygen 2, there are actually 2 different things that you could draw. One of them is a carboxylic acid, ethanoic acid, as shown here, and the other one is an ester. We've just rearranged those atoms, we've got the same number of each of those atoms, and yet we've got a different functional group. The one on the left is a carboxylic acid. The one on the right is an ester, which incidentally would be called methyl methanoate. And then the same thing applies here. We've got C4H8O2. This could be butanoic acid. That's a carbon chain of 4. Or it could be actually one of any number of esters. We could have had propyl methanoate or methyl propanoate, or indeed ethyl ethanoate. That's 3 possible esters that we could have that all share that formula. And so functional group isomers are molecules that have got the same molecular formula but different functional groups as a result of how their atoms are bonded together. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.